So back to the topic of the distance at which we can see targets. The rule of thumb is 1 ton equals 1 nanotesla distortion at 100 feet. By the way, in the parlance of geophysics, 1 nanotesla is also sometimes called 1 gamma. The field that we showed in the previous section actually falls off as the inverse cube with distance. What does that mean? Well, that means when we double the distance, we only have 1/8 of the field intensity, or the distortion to the field. So if we have 1 ton equals 1 nanotesla at 100 feet, another way of writing this is if we went to 50 feet, we would have 8 times larger field. 8 nanotesla. 1 ton. So as we cut the distance in half, we get a larger anomaly. But because it's linear with mass, we can also write this a different way. And that would be that 250 pounds equals 1 nanotesla at 50 feet. Because you see, we have taken 1 ton and cut it down by a factor of 8, and it's linear with mass, so we're seeing a 1 nanotesla distortion. Remember that the cesium vapor sensor, whether it's deployed in a single system or as a transverse gradiometer, is measuring data less than 0.1 nanotesla. So we are able to see the 1 nanotesla distortion quite easily. Let's continue on. With the same relationship, we can get down to, say, 32 pounds equals 1 nanotesla. So we cut that down by a factor of 8, so that means the distance is at 25 feet. So now you think about something of 32 pounds, that's quite a bit of steel. And in fact, we can see it much, much further, 25 feet, than we could see it with any kind of metal detector. A metal detector falls off as inverse 6th power because of inverse cube going out and inverse cube coming back. So the magnetometer has the ability to see targets at a much greater range than a standard electromagnetic type of device. We can go further. So let's take this down to 4 pounds equals 1 nanotesla at 12 feet. Now we can see something that is grapefruit sized at a range of 12 feet. Now I want to talk about some things that actually improve our ability to detect these sizes. Because you remember that I talked about induced fields. So all of this is all based on induced fields with a susceptibility of 10 CGS. So all of these numbers are based just on the material being magnetized in the Earth's magnetic field. But most of these objects that we're looking for, again, pipelines, telecommunication cables, wreck debris, parts of treasure ships, unexploded ordnance, all of these materials eventually will pick up a permanent magnetic field because they've been sitting in the Earth's magnetic field for a long time. Or when they were actually formed in the foundry, in the steel producing factory, when they cooled down, they picked up an alignment, and that's called permanent magnetic field. So the point I want to make here is that induced fields give us the ability to see objects perhaps at, let's say, 30 pounds at 25 feet. But the permanent fields can amplify this response by a factor of 3 to 5 or more. So instead of having a 1 nanotesla anomaly at 32 pounds at 25 feet, we might easily get a 5 nanotesla when we include permanent field. So now it's getting easier and easier to detect smaller items at greater distances, particularly if you have a high sensitivity and high speed magnetometer. The speed is important because we need to get enough readings over the anomaly in order to fully characterize its shape, because it is its shape, after all, that tells us something about its location and its mass.